I am the coordinator of. Thank you, Anna. I am Manjur Murshid. I am coordinating the European Union project response. So the goal of the response project is basically to establish a strategic vision for smart cities, energy transition. We want to be climate neutral by 2050. And the idea is to turn energy sustainability into a vision to solve different types of energy problems such as security, equity, and environmental sustainability at the building block and the city level. Today, in this fourth webinar, we will be focusing on the sustainability aspect. In the earlier three webinars, we have focused on building storage and breed aspects. So today we will have, next slide please, 7 air quality topics, which is very important for the sustainability in cities. And these topics will be presented by distinguished speakers, which are representing 4 response cities. Just to give you a quick look what we are going to hear today. From Turku, Ilkka-Pekka will present the air quality forecasting system in Turku. Then we will have 4 presentations from Dijon in France. First 2 presentations will be presented by Matteo. These are on air quality management handbook, and then the citizen engagement on air quality. Then Olivier Martimo will present the indoor air quality as an example. He will give how the sensors are being employed. Then Nadej Martini will present the outdoor air quality monitoring and forecasting in Dijon. After that, we will have presentation from Zaragoza. Bregon Sanchez from the city will present the citizen engagement, how the students were engaged in order to better understand the air quality. Then from Gabrovo, Svetoslav Martiv, I'm sorry if I pronounced the name wrong, he will present on behalf of the city of Gabrovo, air quality monitoring and citizen engagement aspects. So we see we have lots of different topics on the air qualities in response, and this has been widely researched, and lots of feedbacks and recommendation has been given. Next slide, please. So as we said, this is what I explained earlier. So we will go through presentation by presentation within the time. I am not going to repeat it now again. So we will have the presentation from Turku first, and then from Dijon, and then from Zaragoza. Next slide, please. And from Gabrovo in Bulgaria. So now let's hear the exciting presentations from the colleagues. Thank you.
Okay, thank you, Manjur, for the introduction. As said, I will talk about our air quality solution for Turku that we have been building during this project. It has both model components and measurement components. Next slide, please. So, here. So first to start off, why we are interested about air quality. So an extreme answer for this question would be that even in Finland, it is estimated about 1,600 people die each year from poor air quality. Of course, the exact causes are something like asthma or cancer, etc. But the air quality issues are under there. And from in the case of Finland, the biggest biggest pieces of air quality that affect bad air quality are particulate matter, and especially the particles below 2.5 micrometers. So this is this PM 2.5. Also, in the case of Turku, the benzoypyrene, so this BAP, they're important because there's a lot of household wood burning, although which also creates small particles and so on. The biggest source currently in Turku for these particulate matters is traffic. Next slide, please. Our air quality system for Turku, it's composed of three main components. So first of all, we have air quality models using two different ones. One is called Enfuser, the other one is called Sila.
This meeting is being recorded.
Okay, I think I'm back now. So my connection broke. We are using this PALM model to create high resolution, high quality wind information, which we feed to the air quality models Enfuser or Sila. And then we also have five sensors, air quality sensors that are connected with 5G, and we use this data also to improve Enfuser and Sila functionalities and accuracy. The data that the air quality models produce, we've provided further to other applications. And in the case of this project, it's mostly the air quality journey planner and the City of Turku information platform, this Trimble logs. Next slide, please. So our models, Sila, it's a complicated, very big chemistry transport model, and it has a lot of chemical species, physical transformations, and it works from global scale to this so-called beta mesoscale, so around 1 kilometer accuracy. We can utilize several sources for the wind and meteorological information, such as the European Centre forecasts, but also smaller scale weather prediction models such as Aroma or Hirlam. Next slide, please. This Sila model is operational currently at the Finnish Meteorological Institute. You see the links below there, so if you want, you can. Well, clicking doesn't work, I think, but you can. They're short enough, so you can type them in, and you can take a look what the models can do. But it's operational, run daily, and we produce forecasts for several different species concerned to air quality. And as I said earlier, regarding this project in Turku, the PM2.5 is the most significant. We have done a special zoom for the southwest Finland, so including Turku region, and this is something that works at 2.5 kilometer resolution. And as said, there's one forecast per day, and it's for the next 48 hours, but also the previous 48 hours are visible, so you can see how the air quality was in the past and how it will be in the future. Next slide, please. Our other air quality model is called Enfuser. And this works only at city level. It's a bit simpler model based on this Gaussian plume and Gaussian puff formulations, but it takes different kinds of data sources in account through data assimilation, data fusion routines. The model is currently operational both in Turku and in Helsinki regions. Next slide, please. Here, yes, so the spatial resolution for this model is approximately 10 meters, and we take into account several different emission sources. Including traffic, households, power plant, ships, etc. It's operational, as I said, and run daily twice. And we have
This meeting is being recorded.
Okay, I was dropped. So can you please click the play button on this this video? It's on the yes, there exactly. So let's see if it works. It's a bit jumpy, but this is the PM 2.5 concentration in Turku for a short period of time, and as you can see. The video didn't show up that well, but you can see how the roads are very clearly visible in the Turku region. Okay, next slide, please. Then Palm, our wind model. It's yes, it's a computational fluid dynamics model, meaning that we solve the wind velocities and a few other quantities. And the approach that we're using in this project is called large eddy simulation, so LES. However, this approach is it has very high resolution. That means that it's a very high computational cost. We are running these simulations on supercomputers using some hundreds of cores, and this means that we are not able to use it in an operational sense directly. However, it's very accurate, and especially in the case of cities, we can get the interaction between the wind and the buildings and the trees and other obstacles. And there's also a video. Let's see how well this works. So the play button there, it gives this gives a sample. Okay, yet let's see. It gives a sample on how well what the results from the simulation look like. So these colors, they indicate wind. Black is about 7 meters per second, and white is 0. And this is how the wind over Turku looks as simulated by the LES model. And as you can see, there's a very high amount of detail, and especially the interaction between the buildings and the wind is captured. Next slide, please. And what we are simulating and where we are aiming with this high resolution air quality modeling is a student village in Turku. So this terrain map on the right, it describes the Turku region, and this innermost red square, the student village is in the middle of this area. We are modeling the winds at this area with 4-meter resolution and an 8-meter resolution for a big portion of the other parts of the city of Turku. There's a 16-meter resolution region around all this, but this is a bit too close for proper use. All these models have been built based on the LiDAR data that the city of Turku has provided to us. And during our cases, we're considering different wind direction at every 30 degrees. Next slide, please. In addition to models, as I said, we have prepared particulate matter sensors. These are low-cost sensors based on the Sensirion SPS 30 sensor. It measures different kinds of particulate matter, masses and numbers, and based on the studies done at the FMI, the PM1 and PM 2.5, they are those brackets with the highest accuracy. So we are concentrating on these values, and especially on the PM10, the quality of the measurements is pretty poor. The data transmission has been accomplished through 5G. And the sensor is built inside this plastic 3D printed container. 6 sensors are currently installed, and data transmission is ongoing from these sensors. Next slide, please. So here's the distribution of the sensors in the Turku region. There's 3 points in a very close setting, just slightly up from this Turku sign, and this is where the student village is located.
This meeting is being recorded.
Yes. And then next slide, please. So yeah, here's a picture of one of the sensors and the data it's providing. I think we can go forward. Next slide, please.
2 minutes more, please.
Yes, so let's go forward. So, and what kind of improvements are we trying to get in this project? So this is Turku, and the next slide, if you go forward, it will show how we are treating wind currently for this area. So it's basically one or two. Now we're getting on the better one, but if you see this, so quickly the previous slide, this one. So this is the current state of the wind modeling for the Turku area. So it's very coarse, only few values of wind. And then now if you go one forward, so this is what we're aiming at. So to really be able to represent the interaction between the buildings and the wind and the small details within the wind structure. Next slide, please. We have been able to couple these simulations with SILAM currently, and we're using instantaneous velocities here. And the benefit is that it's really quick to run, and we get similar results to what we see from the LES directly. And this example picture is of a ship moving away from the Turku harbor. Okay, next slide, please. And for end user, we're getting similar good results. Maybe you can play this video while I'm explaining. We are using a different approach with the end user model, though we are applying the average fields from the LES. So it doesn't look exactly the same as the LES, but it's still able to capture the interaction between most of the buildings and add a significant amount of detail to the predictions. And the both approaches, they're very fast and well suitable for operational air quality modeling. Next slide, please. So in summary, we have currently been able to utilize the high quality wind information produced by LES in both end-user and SILAM models. The work is still ongoing, so these high-quality, high-resolution models are not yet operational, and we still need to. We plan to finish them during this year and hope to get them operational sometime next year. The 5G sensor network, the few of the sensors are still to be installed, but we are hoping to get them installed soon. And this data will be used in the air quality models when we finish the model development. And also we need to do some new Palm runs. So a lot of supercomputer time will be still used in this project. And thank you. I hope I was not that much over time, and I'm ready to answer any questions now or later if you have some. Thank you.
Thank you, Jukka-Pekka. I don't see any questions on the chat, so I think we can move forward. So I'll give the floor to Mathieu, please.
Hello. So it's okay? You hear me?
We can.
Okay. We are going to talk about air quality management and more especially about the handbook we wrote for the response project. So next slide, please. Yes, to begin, I propose a quick focus on the concept of air quality management and how we approached this concept in the handbook. The main objective of air quality management is the improvement of air quality. To handle this, there are three linked processes. The first one is the air quality monitoring, to have the most complete diagnosis on air quality. After this, it's important to develop and promote collaboration between different partners, for example, scientists, citizens, decision makers. And finally, to set up actions aimed at improving air quality. So that's the three linked processes. You can switch, please. And the objective, the objective of the air quality handbook is to give some keys, some concepts, some examples to help European cities in air quality management. So next, please. The drafting of this handbook is part of the task 10.4. It's the result of a huge collaborative work led by HATMO with FMI, Dijon Metropolis, the city of Turku, and iSolution. So we'll now take a closer look at the content of this document. Next, please. Here on this slide, you can see the big picture of the handbook layout with 5 chapters. It was written with we want to write it with 3 guidelines. The first one is to provide recommendation and methodologies. Also, we want to highlight the actions developed in the response project, and in a way we want to help replicate these actions. And more generally, we try to present every topics in a accessible and synthetic way. So next slide, please. If we go a little deeper in the content of the handbook, the first chapter is an introduction with background information and a reminder of the methodology and a reminder on the response projects. So next slide. The second chapter reviews a large number of air quality concepts to explain and provide key information. For example, we can find many data on air quality regulatory, or other example explanations on atmospheric pollutants. And to facilitate the reading and the understanding of the handbook, most of the time these explanations are presented in sheets form. So next slide, please. The chapter number 3 and number 4 are about the monitoring of air quality, outdoor air quality, but also indoor air quality. This part is more technical, but it will provide a lot of methods and tools. These chapters contain a lot of examples. You will find more than 15 sheets which details this monitoring tools, this methodology, to be the most comprehensible as possible. Next, please. More precisely, in chapter 3 about outdoor air quality monitoring, 3 fields are covered. Of course, the measurements, but also the methods to evaluate the air pollutants emissions, and finally modeling, forecasting, and or mapping of air quality, like Jukka-Pekka has just shown an example before. Next. Yeah. Here you can see another example of a modeling tool, which focused on coupling between measurement and modeling system. I won't go into detail because this subject will be presented in few minutes by Nadej from a university, but it shows the content of the sheet and the linked explanation you can find in this kind of sheet in the handbook. Next, please. Like I said, indoor air quality is also covered in chapter 4, with general principle to fight against this kind of pollution, and as usual in this handbook, some examples of innovative measurement system. One of these innovative monitoring tool will be presented by Olivier from NanoSense in this webinar just after my presentation. So next slide. The last chapter is more operational, with a presentation of action for a good air quality management. Most of the time, these actions are part of the response project. Next slide. To help with planning this action, we propose an air quality management plan. It's a spreadsheet filled with actions from Turku and Dijon, and which contributes to improving air quality. So the sharing of this template and all the tools or action sheets you can find in this handbook is a good way to outreach the activities on air quality and boost the replication. Next slide. In this last chapter 5, we made different subsections. So can switch, please. So like I said, the shared spreadsheet with an overview of all the action, and for each actions, some key elements like the objective, the result, the financial aspect, or the planning. Next slide. Another subsection which describes several examples of action taken by the two lighthouse cities, action that takes in their urban planning or in their development policies. Next slide. You can find other action focused on coordination and knowledge sharing. And next, please. And finally, action to raise public awareness and empowerment. In this example, you can see the sheet from the CNET action, and I will make a quick presentation of this action just after the presentation of the handbook. So next, so to conclude, we have tried to make this handbook as complete and comprehensive as possible, with the aim of making a decision support tool for a good air quality management. Also, we try to highlight the response action and to make replication easier. And finally, I would like to take this opportunity to thank all the contributors, and a special thanks to Monjour for his deep review, and to Itimat for her work on drafting this handbook. And I hope this quick presentation will encourage you to read this handbook and use it in your projects. So thank you. And I will keep the floor to introduce to introduce an action which aims to raise the citizen awareness on air quality. This action is named Bike as a Sensor, and it is developed with the Swedish company CNET. Now, this action is part of the task 4.2, which aims to implement digital solution to increase citizen empowerment. So this action takes place in Dijon Metropolis. The objective is to develop 25 sensors to deploy 25 sensors on electric bikes in order to measure noise and air quality. So the principle is when one of these bikes will be used, it will function as a mobile sensor for air quality and noise. And all the measurements will be shared on a phone application to provide information to citizens. Next slide. And for now, most part of work was done by CNET to test, to improve the sensor. They work especially for the data transmission and the measurement improvement. The work also concerned apps translation to put the apps in French, or producing the promotion or technical documents to explain how the sensor work. And now we are working with Dijon Metropolis to define the recruitment procedure for bicycles, and we also consider exploring other types of vehicle that can be equipped. Why not electric buses or tramway? So to conclude on this action, we hope to achieve the following objective and benefits. First, providing specific information to citizens during their journey on their exposure on air quality and noise. Also raising awareness by involving citizens in monitoring and therefore increasing their involvement in actions. And finally, using the global interest in new technologies and digital tools to target more habitants. So thank you for your attention.
Thank you, Mathieu. So we will move forward to the presentation of Olivier. Please go ahead. Olivier, are you there?
I think Olivier is not there. Maybe we could collect questions if we have some questions.
Yes, but I don't see any questions in the chat. So I propose to move forward to the next presentation. That will be Nadesh.
Yes, I'm here.
Okay, thank you. Thank you.
Thank you. So I'm going to present the work that we conducted with Mathieu and the team in Atmo for the outdoor air quality monitoring improvement. Next slide. So first, let me remind the first general objectives of the work we conducted. It was initially to provide daily air quality maps and forecasts at a 10-meter spatial resolution at the scale of Dijon Metropolis. And to reach this objective, we based our work on two things. First, in situ measurements from a low-cost microstation network, as in Turku, finally. That we developed in partnership with the Institut de Recherche pour le Développement in Bondy. It means that we developed this microsensor, and I will present the tests we did with this microsensor just after. Second, we use the CIRAN model, which is implemented in Atmo Bourgogne-Franche-Comté. And we coupled the two elements in order to improve the spatial representation of air quality and its forecast in Dijon Metropolis. Next slide. So 3 steps were needed here. First step, the in-situ data collection and processing for the Cameleo low-cost microsage sensor. That's his name, Cameleo for quality of air module for environmental learning, engineering, and observation. So this work was done by University de Bourgogne. Second step, the test with the CIRAN model and the evolution of the simulation platform. This work was done in Atmo. And then the first step was the integration of the Cameleo microsensor dataset into the CIRAN model. And this was done in partnership between university and Atmo. Next slide. I have now a few slides for each of these 3 steps. Step 1, it is about the Cameleo sensor, because we developed this sensor, but it is obviously developed to provide scientific quality measurements, but we needed to calibrate and to validate the provided measurements before integration into the CIRAN model. So that's what we did, because there is still a difference between what we can develop in a lab and what we can implement in a real urban environment, obviously, and over a long time series. So you see on the graph, just on the top here, the comparison between the prototype of the Cameleo sensor and a reference station by Atmo. And it is quite coherent. So the first results are quite satisfactory. Next slide. To conduct this study with Atmo and in the frame of the ASH 2020 project, we selected 4 Cameleo sites because they had a 1-year period available. So that's the first criteria. And also they were representative of diversified typology. So you can see here the list of the 4 sites we selected. Among them, there are 2 sites which are traffic sites and 2 sites which are urban background sites. So they were quite representative of the typical urban environment. Next slide. Then we did statistical analysis on the Cameleo time series for 2 pollutants, PM10 first and PM2.5 secondly. On the figure presented on the right, you can see that Cameleo also measures the PM1 mass concentrations, but I will not go into detail here because the CIRAN model does not provide the PM1 mass concentration simulations, but still it's interesting to mention it. So as a result, for this first test, we can conclude that Cameleo microstations do not have a significant number of missing values. It is estimated between 5 and 6% for 1 year on average, which is quite correct. And these values are generally not consecutive. So this means that the Cameleo stations are able to provide a long time series without any long interruption. Next slide. We then compare the Cameleo microstations with the Atmo reference stations. Here we have the results for the PM2.5 pollutants and for the traffic stations on top and background stations on the other table. What we can see here is that all the correlation coefficients are significant at 95% according to the Brave-Pearson test and greater than 6.4, let's say. So it is quite satisfactory here. And it is quite satisfactory given the fact that these stations are not quite close one from each other. This means that you can consider that given a typology like background or traffic, you have a quite good agreement with the reference station. It is important to precise this. Next slide. It is important to precise that all the data sets we used to compare with the reference stations were raw. And we needed just to apply a similar approach of correction as the one used by the Atmo organization. So that's the method I present here. So this is the classical method which is applied to clean the Atmo data set. This is the 3 times value method. This means that we can remove the values which are extreme compared to the other values of the time series. Next slide. And we compare this with another method, which is the isolation forest, which enable to get a more equilibrated data set because it enables to keep low concentrations as well as high concentrations, but still removing extreme values of the time series. Next slide.
More minutes, please.
Yeah. Next slide. Okay, so here it was just to compare the 2 series of sites, just to see that we have obtained a more equilibrated data set. Next slide, I will go quickly. The step 2, so it was in Atmo BFC to stabilize and optimize the modeling platform. Next step for the PM and also for the NO2 and the ozone. What you can see here is that you have quite smooth spatial variability for all pollutants we consider. Next slide. So these are the different tests that have been done on the CERAN model to stabilize the platform. Next slide. And here is the comparative analysis between CERAN and Cameleo stations. And what you can see is that in winter, CERAN tends to underestimate the results measured by Cameleo. And during the summer period, it is the contrary. There is an overestimation of the concentration. Next slide. So the integration of the Cameleo in situ measurements into the CERAN model enables to give more spatial variability for the PM concentrations, PM10 and PM2.5. Next step. And here you have the results for the 2 seasons we are interested in. First, winter. So you can see here that the levels of concentrations are quite different because you can see a blue map on the right. And you can see that the concentrations of the pollutants in the city center is higher than the ones found out in the CERAN model without integrating the Cameleo measurement, which is quite more realistic. Next step is for the summer concentrations. So here is the same conclusion. It means that globally, for the integration of Cameleo measurements into the CERAN dataset, into the CERAN model, next step, we have quite good results, but still we have to be careful with this integration of measurements, of microsensor measurements, because it integrates mean equations for 1 year long time series for Cameleo, and we need to integrate real-time daily Cameleo dataset in order to reduce the bias for some particular cases. So that's what my conclusion here. So it's good, but we need to improve the process with real-time Cameleo dataset into the CERAN model. Thanks for your attention.
Thank you, Nadesh. Still no questions. I cannot see any questions on the box. So we will move forward to the next presentation. And I will give the floor to Briogan, please.
Hello, Anna. Thank you. Still 7 minutes, right?
Yes.
Okay, great. Thank you. You can zap the slide already. So yeah, my name is Brogan Sanchez, and I work for the Smart City Department of the City of Zaragoza via Zaragoza City of Knowledge Foundation, which is an organization devoted to support in the fields of urban science and urban technology to the City Council. So just to be brief, when we speak about contamination, and it's clearly the title of this webinar today, a global emergency, we can see clearly with infographics like this one, that we are talking about problems and solutions that are produced at the local level, but with a huge global impact. I mean, the pollution is moving constantly. We are just affecting every piece that we are doing in another part of the world. So the point on all this is that in the modern world, cities are now the political change makers. So we need to tackle contamination, we need to tackle education from the city. And it's from the education perspective that this initiative came from. So you can jump the next slide, please. Well, this image is a smoke. It's not it's not a reference of big cities, but any city on Earth had at some point a smoke on it, which has direct implications on society, on climate. Actually, the most vulnerable inhabitants are the ones living in the cities due to the urban heat islands that are increasing the temperature by probably +3 or +5 centigrade degrees in summer. And well, knowing this, we wanted to make an experiment together with 2 other cities in Europe and to raise education and raise awareness on pollution. And to do this, we wanted not just show the externalities of the contamination, but to make people, citizens, participants on the extraction of data, on the interpretation of data, and the visualization of data itself. So the experiment that Zaragoza had carried were with youngsters, children or teenagers between 8 and 16 years old. Why? Because at the end, they are those who will better transfer the knowledge to their parents and grandparents, and they are going to be the ones that will, in the next generation, have kids and be more able to make this education. And also for another side, which is that is specifically this rank of ages that is normally less connected to policies. They still don't vote, or they didn't reach the working age. So they are mostly not part of political decisions. So we found interesting to engage them from early age to the experiment. Next slide, please. For this, we have created a solution based on a wearable. It's a device that you may see here in the bottom right part of the presentation, connected to an application, a very single application that could be downloaded in the phone, and promoting a campaign. So the idea on this, we have made already several tests that you may see here in the screen. The idea of this is to design a campaign to engage, in this case, children. The next test is going to be in a few months, in January actually, with the children involved themselves. And this application, with the campaign design over it, will guide the children to go to different places. It will work like a sort of gincana, so there is a little bit of gamification also on it. And go to a place, push the button, and measure. Actually, if I remember well, there is even no button to push. The device detects that you are in the range, and it starts collecting data. Together with the children, we go back to our research center, and we download all the data, making them being aware of the data they have just collected. I just forgot to mention, this is an initiative under a European project called SocioB that will finish in 1 year from on, and whose outputs are already being processed in different deliverables. You can jump to the next slide. I know I have 2 more minutes. So this is an example of the data that has been just downloaded into the system. We can see here by intensity of color and by number of size, the different measurements taken, which are ozone, which are nitrogen dioxide, temperature, among others, and also particle per million. And we make them see from the places that they have been, which are the ones that have better air quality. And this is linked to factors such as transit, as you may see in the map in the bottom left part. The places that are more connected to the big avenue are the ones that that receive more level of nitrogen dioxide. And most importantly, also, we cross data. We just don't see a single data, but we cross data with it. As an example, there is another experiment we are doing. This is a private initiative, which is called Sound Walk, in which we record also noise, and we can make the match with the decibels, with even the birds. I mean, if we hear birds, it means that we're in an area where there is no externalities, noise, and we can also contrast how the pollution is also affecting on this. Next slide. These are the next steps for the project. So we have done the test campaign, and as I say, in January, we will have a test campaign with the children themselves. And right after, the activity will be replicated in 2 municipal schools to, at the end, elaborate a didactic guide for replication activities beyond the project. Next slide. And this will be the last one, actually. And we have the connection with our PD, which in the framework of response is the district that we plan to deliver innovation elements to ensure positive energy consumption. The connections are mostly linked to the environmental holistic compensation of the natural spaces, to make a bottom-up education, not only in energy, but also in pollution and noise, and make Ethiopia as reference centers for early age technology education, among others. Finish.
Thank you. I see here one question. I will do it very quickly before moving to the next presentation. How about data privacy problems? Did you have any problem to collect the consent to get any data on minors?
Thank you for the question. It's a very good question. Actually, there is the data is completely anonymized. We don't have data from the name of the children, not the address. So when the children are being tested to work in this project, they have already a declaration signed by a tutor that we are not using any sort of privacy data other than the localization, which is not linked directly to the child. Actually, the localization is linked to just a number, a very random number that is downloaded in encrypted mode into the application. So for this, we have followed the principle and ethics, and there is no problem in this sense. Thank you. It's a very good question, actually.
Thank you. So we have to move quickly to the next presentation. So we are running the time. So please, we can start with the example of the city of Gabrovo.
Yes, hello everyone.
Oh, thank you.
Nice to meet you. My name is Svetoslav. I'm an expert in environmental monitoring in our city. Can you move to the next slide, please? So actually, we are developing a system, a solution for the air quality, but our general idea is to include other categories of the environment, such as noise and radiation and water quality. But for now, I mean, the solution that is developed is mostly covering the air quality area. So we have 12 air quality stations positioned in different locations of the city, including the industrial zones, the parks, and the central city part. We're monitoring 16 parameters, starting from the PM1, PM2.5, PM4, PM10, also the volatile organic compounds, even though they are not, it's not normal to measure the volatile organic compounds in urban areas. But anyway, the sensor is inside the station, so we're measuring this parameter as well. And in fact, we're using a Sensorion sensor, like before in the presentation, one of the solutions used the same sensor. We're using AlphaSense sensors for the gases and Bosch sensors for the metal data. I will try to share my screen. Can you please, someone of the organizers, allow me to share the screen?
I think it's not possible to share the screen.
It's
as
not possible.
Anna, yeah, you can go through.
Okay, no problem. So the data comes in real time. Our solutions that we implemented transmit data on each 30 seconds. So we have a lot of data in the municipality, billions of records on our databases. We can analyze the data even on a minute level, and the systems that we developed, they inform us about the regulatory compliance based on the latest European regulations and their quality directive as well. We are calculating their quality index. And the most important part of this solution, can you switch the slide, please? I want to just show you how the devices looks like. They're compact devices, but very high class. They're designed and developed by a local company here in Gabrovo, and you can see how they looks like. The next slide, please. For us, it was even more important to create engagement. So actually, we are transmitting the data in real time through a few different digital channels. One of each is the Gabrovo Green portal, where all citizens can enter and can check the air quality. They can check the air quality index recommendation for outdoor activities, and this creates a lot of engagement in the whole municipality. The next slide, please. Also, apart from transmitting data directly through digital channels, we have installed 4 interactive screens in 2 schools in the municipality and in the Technical University in Gabrovo. So these screens, they're transmitting data, they're broadcasting data 24/7. And the citizens and everyone, when they pass through these screens, they can see an interesting fact about the environment. So we have more than 100 facts, and you always see a new fact, and this increases your knowledge about the climate and environmental problems, and this creates a lot of engagement as well. Yeah, this was in short. I don't know if I have more time, so I'm open to questions.
Yes, thank you so much for the presentation. I don't see any questions on the chat, but just to let know that if you then want to make any question to any of the speakers, you can contact us and we will put you in contact with them. So I think we can conclude this for today. Bonjour, please.
Yeah, thank you, Anna. I think there is a hand raised from Dominic Roggo. If you could like to speak up, you could do, I guess.
Sorry, you can speak now.
Yeah, can you hear me?
Yes.
Yes.
Okay, yes. I just had questions to Brogan Sanchez. I found quite interesting approach to have kids to make measurements and in different places and follow that. I was wondering, this device that you have developed or made available, is it very robust and is it very accurate? That's first question. And then second question, do you do that this trial in other cities or only in Zaragoza?
Thank you for the question. So maybe if you can go, Anna, to the slide 73, if I'm not wrong, so I can just illustrate it. So for this, yeah, the test we have made, yeah, this is the what you can see here. Well, we call it wearable, even if it's a size of a potato, but you can actually put it in your bag and in your your backpack, which is a little bit how the children will carry it. We have proved and we have calibrated, and it seems to be very accurate when we contrast it with the data, official data from the Meteorological Institute in Spain that has several positions in the city of Zaragoza. So answering to your first question, yes. And for the second question, we are in collaboration with two other cities in Italy. One in Italy, sorry, and one in Greece, which are Ancona for the case of Italy and Marousi for the case of Greece. They both use the same device. Actually, it has been developed by one of the partners of the project. And what changed only is the target. So while we are working with children, with youngsters in this case, in Italy they are working with commuters. So several volunteers has been selected that are traveling either by train, by car, by bus, by walking, or by bike, which actually match quite a lot with the project that Matthew presented before, like bike as a sensor. And for the case of Greece, the city of Marousi, what they are targeting is the general population with a little bit of focus on elderlies. So for now, the test has been given quite accurate information on this, and at the level of at the micro level, when we are testing with 10 or 20 devices at the same time, there is not deviations between or significant deviation between one place and another. It also depends where you put it and where the wind is coming. So there is always a little bit of margin of error, but in general terms, it has been achieved. Thank you.
Very good. Thank you.
Thank you. I think we are 4 minutes up over the time. I will take just only 1 minute. I would like to really thank you, everyone, especially the presenters, the 5 presenters who have done a very good job in presenting mainly on the 3 main topics. So we had the topics about monitoring and forecasting in Dijon, Turku, and Gavrovo. Then we have citizen engagement with 2 examples in Dijon and in Zaragoza. And then, most importantly, we have also got the review or overview of the air quality handbook from Matteo on the city of Dijon, but this could be applied in any cities which can be used by the stakeholders like cities or policymakers and the stakeholders. So I think we have a very good overview on the topics of the air quality. So we are working on this topic in our 8 cities, in 8 response cities. So the webinar will be recorded, has been recorded already, and will be published in the YouTube channel of Response Project. So you will have a look into the presentation also in the Response website. So by saying this, I say goodbye and many, many thanks for your participation.
Thank you.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.
Thank you. Bye. Bye.
Thank you. Bye.